It's very slow. The system is extremely slow today. So wait. There's a long delay.
Professor, it shows us that the recording is in progress.
Yes? Wow, it's my machine which is slow then. Yeah, my machine is slow. Okay. All right, so let's start. Gregory, do you want to say something?
Yeah, I just had a question about the message that you sent us about the exam scores. You said that you can choose.
No, we should talk about this at the end of the lecture.
Okay.
All right, so we were dealing with parallel form of transfer functions of the type of a general rational fraction. And the last time we covered the case where the super case 1, where m is less or equal to n. No, I'm sorry. Big mistake. Less than n. So super case 2 now is what is left to be considered when m is larger or equal to n. So this includes the case where it's equal to n. So in this case, how do you perform the parallel form of g of z? So you cannot apply partial fraction expansion like in super case 1. So you know that you have to lower the degree of by long division, and then what you get after the long division, you have this new expansion where the degree of r of z is less than the degree of a of z. We call this g naught of z. Therefore, if you take the inverse z transform of this, you have that g of n is q of n plus g naught of n. Therefore, the system of impulse response g of n has this equivalent form which is a parallel form, but where you need to implement these two subsystems separately. Now q of z, we saw that q of z was of that form of a polynomial, so q naught plus q1 z inverse plus q n minus n z to the minus n minus n. And this implies that q of n is a finite sequence going from 0 to m minus n. Where this is q naught, q1, etc. until q n minus n. And that, you know that a system of impulse response like that can be implemented by FIR system. So you FIR system implementation. Meanwhile, this subsystem has transfer function g naught of z that satisfies super case 1, because the degree of the numerator is less than the degree of denominator, and we saw in this case how you perform parallel form of this transfer function. So this one, you perform the parallel form implementation from super case 1. All right. So this is involved because you will have to go back to super case 1 and go through everything. So if I want to be nasty with you at the exam, I will give you a transfer function like that with m larger than n or equal to n, so that you have to go through super case 2, and then I will ask you to perform the parallel form implementation, which will force you to do a long division first, to extract the quotient, and then to perform its FIR implementation. So you cannot forget about FIR implementation. And then for this one, for the second subsystem, you will have to go through super case 1, and if I want to give you mistakes, I will put some complex poles and some double poles, so that you have several cases combined within the same question. And then maybe like a third degree denominator, so that you get everything. You have a pizza with everything on it. Do you like pizza with everything on it?
No.
Oh, I thought everybody. Yeah, no, you don't like pizza with everything. No.
Not
No.
anchovies.
Yeah, oh, not anchovies. All right. So maybe I will avoid anchovies. One topping, if it's free. Yes. It will be free pizza with everything on it at the exam. No, okay. No, I try to give you things that are not so complex. No, well, I should say complicated. Complex, yes, you are going to get complex numbers, but the goal is not to test you on algebra, because this is not math class. Okay, so I will avoid too much complication at an exam. All right, so this actually concludes parallel form implementation, which is the most difficult type of form to implement. So before going to the next paragraph, I would like to teach you some convention that is used by signal processing people that you should learn about. Is that suppose G of n is the impulse response of a system, then we already know that its Z transform is called transfer function. So the convention is that whenever we talk about LTI system of impulse response G of n, the convention is to also represent it like that. That means instead of writing in the box the impulse response, we write the transfer function. But be careful. This is exactly the same thing as this. It's just that we have changed the sticker, right? You know, it's like it's like your favorite cereal. Sometimes they change the cover, and they say different presentation, but same great taste inside. So this is different presentation, but same great taste inside. Okay, it's the same LTI system that you are used to. Is your favorite LTI system the same inside? So which means if you see this, then the input x of n will become y of n equals g of n convolved with x of n. All right, it's still the same thing. It's like a sticker we have changed. I like to give the example where when I buy sugar, I like to from a cardboard box, I like to pour it into some glass container, like the ones you use for jam. But then on top of it, you put a label. So I write sugar, but I could write in a different language. For example, asuka. It's just the name that changed, but inside is the same great taste of sugar. Or I can write sucre, but still same great taste, right? Sugar and sucre, it tastes the same inside. Now, mistake is a mistake is to say to write something like that. When you see this, okay, if you write this, in general, as soon as you write an expression that makes time and z domain in the same formula, you are going to get shot. I typically see y of z equals y of n, or y of n equals y of z. You cannot write this, you get shot. Okay, now an example. Let's see if you understand, you have understood this. Suppose you see a box like that. If I input x of n, what do I get here? Are you able to answer this question using that definition? Okay, I'm waiting for answers. One, no. Waiting for answers. X of n, no. Shahana, You want to say something?
Is it a delay element?
But why is that? Why is that? Gregory, you have just been shot. All right, so I was wondering if you say delay element because you saw it in the book or because you see it as a consequence of what I just explained. All right, I give you the answer. When you see this, you have to understand. Okay, do you see the cursor when I do this? No, no, you don't see it. When you see this, you have to understand that this is where g of z is a z transform of g of n. So okay, I repeat. So you want to look at this as g of z equals z. All right, so this is the same thing as, so this is g of z, where g of z is e to the minus 1. Okay, so that is easy to understand. Now, according to what I said, this is the same thing as this. But what is g of n? When g of z is z inverse, what is g of n? Yeah, so I saw an answer, but now answer this question. What is g of n when g of z is e to the minus 1? Sorry, I saw some answers, but they disappeared. You get impulse response. No, impulse response, you still don't know what it means. Yes, so what is g of n? I'm asking, no, g of n minus 1. No, what's that? Delta n plus 1, delta. What is delta? Delta n plus 1, I understand, but this is wrong. Delta n minus n naught. What is n naught? There's no n naught here. Okay, z inverse, you get shot. Because the question is in the time domain. X of n minus 1, no. It's all wrong. It's all wrong. Yes. Delta of n minus 1. Is delta of n minus 1. So this is the same thing as this. Understood? Because this is the z transform of this. All right, now next question, what do you get here? No, Shahana.
X
Okay,
of n minus 1.
yes, x of n minus 1. So somebody wrote this before, but it was not the answer to the question of before. Now this is the answer. All right, so this is the same thing as. Did you understand the reasoning? This system is the same thing as this system, but we express here the impulse response, while here we express the transfer function. And then you know that here you get x of n minus 1 because of this. And then yes, then we get back to Shahana's answer. This is the same thing as delay element. All right. So this notation is is actually used in every book. This brings me to the last section of chapter 2, which is analysis of random systems, random. All right, so what you have seen so far is very organized feedback systems. But what if you give to a baby small LTI systems to put together like a Lego game? But you give that to a baby. What are you going to get? You get you are going to get something like that. In fact, to obtain something like that, the baby has to be of a certain age, because you know that the baby has to be smart enough to make only one input and one output. But if you give that to a younger baby, you might end up with a system with many inputs and many outputs. The thing is that multi-input, multi-output systems, they do exist, and it's not taught at this level. This is taught at the graduate level in a course called Linear System Theory. Note the word theory, the scary word theory, which we don't teach here, fortunately for you. But question is, what is the impulse response? What is the difference equation? Is it stable? These are the questions that we need to answer. All right, so I'm going to give you an example, because obviously I'm not going to be able to deal with this system. So let's work with something more explicit. Suppose you input your sequence into a LTI system of impulse response f of n. And suppose this is a very complicated system with maybe in some of the forms, direct form 1, 2, cascade, parallel. But to give you some headaches, I'm going to put a feedback, and within the feedback, I put another crazy LTI system. But then, to give you even more headache, I put a feedback inside the feedback, and within the feedback of the feedback, I put another LTI system, another crazy LTI system. And then I ask you, oh, what is the impulse response? Or is it stable? How are you going to do it? Let's write what we can write. What is y of n? It is the output of this system. So it is f of n convolve with the input. What is the input of f of n? It is the sum of x of n and the response of the system. But what is the response of the system? It is g of n convolved with its input. But what is the input? It is the sum y of n plus this signal. But what is this signal? It is h of n convolved with its input, which is the response of g of n, which is g of n convolved with its input, which is the sum of y of n, and the response of h of n, which is h of n convolved with g of n, convolved with the input to g of n, which is y of n plus the response of h of n, which is h of n convolved with g of n convolved with y of n plus h of n convolved with g of n convolved with the input, which is y of n plus h of n convolved with g of n convolved with y of n plus h of n convolved with g of n. Hey, hey, you are going to let me die? Yeah, you were just letting me die. Okay, so what can we do then? Okay, I'm going to give you the trick. There's a trick. We don't, here there is some signal. We don't know what it is, but I'm going to call it W of n. It's unknown, but we can always inject some unknown variable provided that we find some extra equation. All right, so that means instead of just writing one equation to find y of n in terms of x of n, maybe we can find two equations involving y of n, x of n, and w of n, and then we can try to eliminate w of n. So first equation, y of n equals f of n convolved with the input of f of n is x of n plus w of n. All right, so this is correct. This is correct. This is one equation that is correct. But since we want to get rid of w of n, we wish to have an equation involving w of n. Now, but the w of n is what? Is going to be g of n convolved with y of n plus the response of h of n, which is nothing but h of n convolved with w of n. And we start. It's not endless. However, w of n, we don't know what it is. But what we can try to do is extract it from w of n. So what I'm going to do is that I'm going to put all terms in W of n on the left side. So on the right side, you end up with G of n convolved with Y of n. But then you have G of n convolved with H of n convolved with W of n that I'm going to put on the left side. And then I'm going to factor out W of n. But I'm not telling you what is here. You tell me, but with the danger to get shot. Hey, as soon as I say danger to get shot, nobody answers. Okay, 2 years ago, yes, I see answers. Yes, Gregory got shot. Sorry, Gregory got shot. Yes, neutral element. So explicitly is the neutral element. Somebody said neutral element. All right, so what is the neutral element? Yes. So Gregory said 1, and that is the shooting answer. That is shooting answer. All right, so it's delta of n because when you re-expand it, delta of n convolved with W of n gives you W of n. All right, so now we want to get W of n, all right? All right, so you want to what? You want to what?
That's yeah. You want to do that convolution division thing.
The what? The what? The
The
what?
division sign with the convolution symbol mixed with it.
Convolution. You mean the this thing? The divi This is what
Yes,
you
sir.
mean? So so this is something we can do in reality or only in a dream?
And the dream Z transform dream.
Yes. Good. You have learned the lesson. Yes, we wish to do the division, we cannot do it. So we go into the Z domain. Because now in Z domain, you know that convolution becomes multiplication, and this is exactly what you want. All right. Gregory, what should I put here? Yes. All right. So you got shot. Now you get revived. So this time you can say 1. So eventually you get. Now you can do the division. Now you can do the dream division. Now, since we're in the Z domain, we cannot inject W of n here. We cannot inject W of Z. So we need to write equation 1 in the Z domain. And then we can inject W of z. Now here we have W of z times f of z. So what you are getting is this. Times f of z. And then you want to have y of z in terms of x of z. So you are going to get, I'm going to put the y's on the left side. And then clearly you can get y in terms of x. And what you have here is the transfer function. I'm going to call it L of z. And that is the transfer function of the system. And of course, if the question was, what is the impulse response? You need to go back to the time domain. And that is the impulse response. But you have to imagine that each subsystem is a complicated LTI system. So you have to imagine that f of z is itself, this system is itself a complicated LTI system, maybe in direct form 2, or parallel form, or cascade form. This one is another such system, and this one is another such system. And then the global system has a transfer function like that, and then you have to perform the inverse Z transform. Will you commit suicide? Interestingly, this morning, one student said, yes, I will commit suicide. But here, you are strong. So the answer is no, because regardless of how your subsystems were given, f of z is going to be also in the form, you can always put it in the form of a rational fraction. Same for g of z. Same for g of h of z. So you end up with fractions of fractions of fractions. What happens when you have fractions of fractions of fractions of fractions? You learn in kindergarten, maybe not. In primary school, maybe not. In junior high school, that if you have fractions of fractions of fractions, you can do flips, 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 and then the whole thing in the end becomes one single fraction. So in the end, this can be just one fraction. And with this fraction, you can do whatever you want. You can find the inverse Z transform using partial fraction expansion, or you can re-implement it using direct form 2, or parallel form, yes. And stability, you look at eventually you look at the poles, and you get stability, right? Now, I would like to teach you a better method. What do you think I'm going to write here? Do you know what I'm going to write here? Semi-educated? Ah, that's funny. Same answer as this morning. No. Professional people. Wow. I'm going to teach you the method for professional people. Sounds good, huh? It looks like a joke, but this time it's not a joke. It's really what I experienced when going to conferences. So quickly, I'm going to show you what is the method for professionals. Because you are going to become professionals very soon. Professionals, they say the following. You're about to write that y of n is f of n convolved with its input. If you can write this, then why not write that immediately in the z domain? Because it's so easy. In the z domain, y of z is going to be the transfer function times the input in the z domain. But z transform is linear, so the input here is the sum of these two inputs. So in the z domain is also going to be the sum of the z transforms. It's so easy to write this. You see, if you can write it in the time domain, why not write it directly in the z domain? You just need to map convolution into multiplication, and addition is still addition, right? So it's free. You can do the same thing for w of z. G of z times y of z plus the response of this, but in the z domain is going to be h of z times w of z. And then you, from equation 2, you can isolate, I'm going fast, you can isolate w of z. And you continue the same way, right? You then w of z is g of z divided by this, and then and then you continue the same way. Continue. The same way as above. All right, so I'm not kidding when I say method for professionals, because in the really professionals, they use z notation all the time. So they use this other convention where they put f of z, g of z, h of z directly. And I can give you an anecdote. When I was a young engineer working in a company, they sent me to a conference about circuits, and in this conference, everybody was using z notation only. And at that time, I just didn't understand. I just didn't understand what was happening. But the problem is that when you are sent by a company for a conference, you think it's vacation, but it's not, because in the end, when you return, you have to make a report and give a presentation, and I was in big trouble. So to tell you the story, what I did is that I BS'd my presentation. Okay, I know it's not good to say that, especially from a teacher. Yes, I agree with you, LOL, yes. But the funny part is that I don't know how you say that in English, but they liked the presentation. So I managed to get away from this problem. And but the reason is that when I studied EE306, well, in my school it was not called EE306. The teaching was really bad. So okay, you may say, oh, bad excuse. But anyway, this is telling you that this is real stuff. If you meet people, they are not going to even ask you if you know the Z transform. It's like they speak Z transform like they speak English. Okay, end of chapter 2. Is it good news? Okay, 15 people responded. Okay, somebody say I don't know. 25 people responded. Okay, so let me show you the response. 16 people say no. 10 people say yes. So the 10 people, they don't like chapter 2. And 16 people, they say, no, it's not good news. Why is that? Isn't that good news? Can somebody say why they said no? No? Okay, the bad news, yeah, it's not good news because it's in the exam 2. I can tell you another answer. Oh, it's a good chapter. All right. I can give you the answer of somebody from this morning who voted no. He said because there's no good news in EE306. All right. Now, yeah, don't vote yet. Hey, wait, don't vote. Okay, let's do it again. Don't touch. All right. So I'm going to ask you the same question. Is end of chapter 2 good news? But after you see the title of chapter 3. All right. So is end of chapter 2 good news? Sorry, I cannot help laughing. Now I'm seeing a huge majority of no. All right, I'll show you the answers. All right, now it's lots of no when they see the title of chapter 3. But six guys said yes, it's good news. Okay, you are going to see something. Did you notice how convolution appeared in this class? It was not like I came to and say, okay, I'm going to impose to you that formula of convolution and no choice, you have to deal with it. No, it was not like that. It was more like it popped up by itself. you'll be amazed that Fourier transform is going to pop up by itself to the point that you're going to say, oh, I could have derived it by myself. You'll be surprised. But to understand that, we need to go through a first bad news, which is the following. Does everybody see the comments, those chat that I see? Everybody sees that? Yes, everybody sees that. Okay. All right. I'm not going to repeat that what he said. Everybody saw it. Okay, so what is the motivation? Many students, when they go through chapter 1 and chapter 2, they get really tired because they say, where are we going with this? I mean, where is the engineering part? It's all algebra, formulas, and what do we do with this? And what's the application of this, right? So the problem is that until now, you only know that an LTI system performs this operation. But then you can ask, so what? Right? You could say that, so what? What do you do with this? The problem is that you may understand this algebra formula, but you may not know what it does physically to the input. That's the problem. So, and the thing is that it's very difficult to be able to anticipate what the system is going to do on an input just with this convolution, just from this convolution. But it's as hard as when we deal with matrix multiplication. You know, when you do matrix times a vector v, the formula is complicated. You know, even in 3 dimensions, you know, a vector v is something you can show with your finger. All right, it's a vector. You can show it in the space. Now, when you see the matrix, are you able to see from the matrix where your finger is going to move, assuming that your finger is going to show what is going to be the transformation of v? All right, so now, so to simplify the analysis, people like to do something. Look for special vectors, that are unchanged by m up to scaling. Meaning vectors such that when you transform the vector, you find itself, however, with possibly some scaling. If you could find these vectors, it's going to simplify the analysis much more, because it just says that the vector keeps the same direction. However, it may be scaled. Okay, so we have to allow something, but if you can find vectors, that will be very interesting, because it gives you some idea about what the matrix is doing on the vector. So if such a vector exists, it has a name. It's called Oh yeah, I forgot to say it has to be non-zero because the zero vector always satisfies this. Then V is called eigenvector. Lambda is called eigenvalue. All right, so who studied that before? You studied this before? I see that a majority of you studied, but there are two who didn't study that. Three? Okay, it doesn't. All right, so this is the answer. Normally, you should have studied it. It's a basic algebra. So, same question for LTI systems. Can we find x of n such that this just gives you the same sequence, but up to a scaling factor? If you can find such a sequence, then knowing what is lambda is also going to be very informative. For example, suppose lambda is equal to 2. It means that there are certain signals which gets amplified by the system by 2. Amplified. Do you hear what I said? The word amplified. Sounds like electrical engineering, doesn't it? Yes, it's nice. It simplifies the analysis, and maybe you can find other signals which are also eigenvectors where lambda, let's say, is small. In this case, we will say that the system filters this type of signal, filters out, right? Then, for the first time, we can stop talking about a physical sense of what is happening to your signal. All right, so we're getting closer to what you expect from electrical engineering. So in that sense, this chapter is the most important chapter, I will say, of EE306. But can we find them? Can we find these eigenvectors? We're going to stop slowly. We're going to start with the delay element. So can we find x of n that is transformed into itself time a scaling factor with a delay element? Okay, vote. All right, 10 people voted. 15, 20, 25, 28. Okay, I show you the response. All right, so a lot of people said yes, but then can somebody tell me, give me an example? Yes, because this wouldn't be a topic. Yeah, Yeah, this type of a guess is not very interesting. No, I want something more. I want more. I want more content. I want some more substance. More substance. If it's just guessing, yeah, it's no fun. It's no fun. There's a simple example. I mean, hey, come on. There's an example that is so easy. All right, you don't see. Okay, it was like free guessing. Okay, no, it doesn't count. Take x of n equals constant. If you delay it, what do you find? Hey. Hey. Yeah, no, yeah, but how much is it compared to x of n? Yeah, you get the same thing. Yeah, the same constant. All right, so isn't that an eigenvector? Yes. So this is eigenvector. And this is eigenvalue. All right, now I have a harder question. Can we find eigenvector of eigenvalue lambda different from 1 wait, I'm not doing this correctly. We find eigenvector of the delay element of eigenvalue which is different from 1. Is it possible or not? Uh, 10 people replied. 15. 19 people. 20. Okay, 2 more answers. No? All right, I show you the answer. All right, so this time it's more splitted. Look, suppose I plot something that doubles every time. 1, 2, 4, and it continues like that. And here it's 1/2, 1/4. All right, so and so forth. All right, you double every time you go to the next one. So in this case, x of n, you can write 2 to the power of n for all n. It continues, right? I cannot plot. It's 4, 8, 16, 32, etc. And inverse of this the other way. What happens if you shift this to the right? What happens? 4 gets replaced by 2. 2 gets replaced by 1. 1 gets replaced by 1/2. So what happens? Each number is replaced by half of it. Each number gets replaced by half of it. You see that graphically, right? Because this sequence is such that the predecessor to every sample is half of it. So if you shift to the right side, yes, I agree with you, it works. Yes. In fact, you see it graphically, but you can see it mathematically. X of n minus 1 is 2 to the n minus 1, which is 2 to the minus 1, 2 to the n, right? Which is x of n divided by 2, right? So lambda is 2, is 1/2. Now, in general, take x of n equals lambda to the minus n. Then what is going to be x of n minus 1? Is going to be lambda to the minus n minus 1, which is lambda to the minus n, right? Which is lambda x of n. All right, so lambda to the minus n is eigenvector of delay element of eigenvalue lambda. But let's go into more complicated systems. Okay, I'm going to save this file, and I'm going to go into FIR system. All right, so to get the FIR system, I'm going to copy from previous FIR. I'm going to copy from previous file. All right, can we find eigenvectors for FIR systems? I see that the majority says yes, but it seems that it's always the same way. It's because if I ask the questions, there would be a no. There wouldn't be a no. All right, so I give you the answer. In fact, the answer is as follows: is that answer if x of n is an eigenvector of the system. No, if it is an eigenvector of the delay element, of eigenvalue lambda, then it is an eigenvector for the FIR system. And I'm going to show that to you. Because in this case, what happens? You're going to get lambda x of n here, right? But can somebody tell me what you are going to get here? What are you going to get here? Can somebody tell me? Quick. Hey, yes, lambda squared x of n. And here you get lambda cubed, and here you get lambda to the power of n, x of n. So y of n is what? It's going to be alpha 0 x of n plus alpha 1 lambda x of n plus alpha 2 lambda squared x of n plus alpha n lambda to the power of n x of n. Now I can factor out x of n, right? But to go fast, it's going to be x of n times something. I can put it in summation. You see, you get lambda k, alpha k lambda to the power k, alpha k lambda to the power k, where k goes from 0 to n. This is a new number alpha, which is the eigenvalue of x of n for this system. X of n is an eigenvector for delay element of eigenvalue lambda. Then it is still an eigenvector for FIR system, but different eigenvalue, which depends on lambda with this formula. All right, so now I'm going to consider case 3. I'm going to consider any LTI system. Or let's say I'm going to call it alpha. Can we find eigenvector for case 3? And the answer is yes. Same thing. In fact, the truth is that it's going to work for any system, not just the FIR, but any LTI system. And the reason is as follows. Is that y of n is what? So what we have what? We know that y of n is the sum of h of k, x of n minus k, but we know that x of n minus 1 is equal to lambda x of n, because by assumption. All right, so x of n minus 2 is lambda squared x of n. In general, x of n minus k is lambda k x of n for any integer k. So here, what do we have? We are going to have sum of h of k lambda to the k x of n. Now look at this. What's happening here? This is a sum over k. This depends on k, right? However, the shift has been transformed into scaling. So x of n is no longer dependent on the shift. Is no longer dependent on k. So what do? You factor it out. You factor it out. And that is your eigenvalue. All right, so what is the important thing here? Fact, what's happening is that the shift has been replaced by scaling because the addition, exponential function transforms time shift into scaling. Right? Because time shift is what? Is addition to the exponent, but addition in the exponent becomes multiplication, as you know. So exponential function transforms time shift into scaling. So that's the reason you can find all these eigenvectors. But I'm going to conclude with this sentence. This fact, exponential function transforms time shift into scaling, is what makes EE205 and EE306 and even engineering 204 work. If exponential functions didn't exist, you wouldn't have engineering 204, you wouldn't have EE205, you wouldn't have EE306, and you wouldn't have Professor Nguyen. All right, so that concludes the lecture. And now, if you have questions, you can ask me. Gregory, you want to ask something?
Yes. With regards to the message that you sent us about the exam, when you say that we can choose the score from midterm 1 or midterm 2, if you choose the score from midterm 1 or midterm 2, are you going to use the scale from the respective midterm, or are you going to like normalize the two midterms to determine like the rank for?
Yes. So what I'm going to do is that I'm going to normalize the two exams so that the class average are aligned. All right. So this is going to modify your grade, and then I will pick the highest grade you have after this alignment.
Okay. So you're gonna, and then the histogram that you're gonna give us is gonna be histogram for both exams, I guess.
So each exam is going to have its own histogram, and then I'm going to scale the two histograms so that the averages they match.
Okay.
In fact, I can give you a little more details. Since some people have negative points in this histogram, I will first shift the histogram to the right. So you see, time shift, right shift.
Yep.
Right, so that the all numbers become positive, right? And I will do the same thing for the second midterm, and then I will rescale them so that the class average of the two match, coincide, and then so each of you will have a new score, and I will for the two midterm exams, and I will pick the highest of the two for each of you.
Got it. Thank you, Professor Tom.
Yes. So, somebody said I love time shift. Just drop midterm 1? No. I will not do that because some people who got good grades in midterm 1, they want to take advantage of their effort in midterm 1. So no, I will not drop midterm 1. Thank you. Okay, if there's no more question, I'm going to start the video recording. One more question, Gregory. The homework is due tomorrow. So tomorrow we have class, all right? You understand that? Tomorrow is Wednesday schedule. We have class, so you have until tomorrow for returning homework. 6.
Professor, I just wanted to clarify, the midterm 2, is it only on chapter 2 or
Yes.
it also includes part of chapter 3?
No, chapter 2.
Thank you.
Is that good news?
And I don't know, I'm still uncertain about that. But thank you.
All right. Thank you for saying yes. Again, somebody this morning said there's no good news in EE306. Number of questions, it doesn't matter. It doesn't matter. Yes, same format, yes.
So 18 questions, you mean, with the MCQ, like multiple choice?
Say it again.
You said same format. Does it mean that you will also have like 18 questions multiple choice, or you can increase or decrease question numbers?
It is same format in the format. Number of questions, I'm not sure, but format, yes. Same format.
Professor, another question. Are